that has become muscle memory that we need to break, some bad habits that we need to break. So here are just some representations of things I'm still seeing as of yesterday. So let's just try and understand. Let's critically evaluate them and try and figure out, okay, what's going on. Because everything is supposed to say something to us. Isn't that the whole purpose of writing reactions and mechanisms and things like that? Mm-hmm. Right, so first of all, can someone please remind me, what is the purpose of curved arrows?
Show electron movement.
Only electron, not atoms. Isn't that right? Mm-hmm. When we show curved arrows, it's trying to tell us how the electrons are moving. Of course, depending on how the electrons are moving, either new bonds are being formed, bonds are being broken, blah, blah, blah. Agreed? Mm-hmm. But only electrons. Okay. How many electrons make one covalent bond?
2.
So you got to keep track of that. Can someone tell me what's going on here?
A double-headed curved arrow.
Okay, why don't you guys think about this everybody, think about this for a minute or two and tell me, what is the problem here?
There's no, it should be a single one and it should go to the plus because that's where
How many total electrons do you think the curved arrows here are demonstrating being part of this process? 3. Mm-hmm. 3. Because that's 2 electrons, here is 1 electron, as you said, absolutely. But then where is the 3rd electron going? So you got to keep track of those things. Second thing, there will never ever be a mechanism, never ever any mechanism that has both double-headed and single-headed arrows in the same mechanism. It can't be. Either a mechanism is a single electron process throughout, or it is a double-headed curved arrows throughout. You will not ever have any mechanism where one step is double-headed but the next step is single-headed, and then no, we can't mix the two. Either it's a radical mechanism throughout or it's an ionic mechanism throughout. Everybody okay? What about that one? What's the problem here?
We're not.
So first of all, we cannot mix those arrows. You cannot have a mechanism with double-headed and single-headed curved arrows in the same mechanism. Not possible. Okay, what else is wrong here? Hydrogen is, but that's what this is saying, right?
Yeah.
You want both the electrons to go to the bromine.
You want both electrons go to the bromine? So once again, exactly.
The bond breaks.
The electrons are not adding up. It's not just about atoms. It's about the whole thing you got to consider. Is that even reasonable? So absolutely. This is good because the two electrons are being used to grab a proton. So what's happening to these 2 electrons? Is one going to hydrogen?
No.
No. They're both 2-headed going to Br. What will be the outcome when that happens? Again, count your atoms, of course, but you also got to count your electrons. Otherwise, there's something wrong with the structure. Isn't that right? Mm-hmm. Everybody needs to be paying attention to that. What about here? What's wrong?
The bond that's broken does not go straight to the.
Well, that does. The electron with the hydrogen goes and pairs with the electron with chlorine.
We need the other
exactly.
arrow.
Where's the other electron?
It's going to the left.
You got to show it. It's not an assumed thing. No, you got to show it. Where did the other electron go? Well, that one went to the carbon. You got to show it. Everybody does that sound okay? You got to pay attention to these details, otherwise you're not really telling what you're supposed to be telling. It's not just the atoms, of course atoms matter, it's also about the electrons. What's wrong here?
Single-headed curved arrows are used. That leads to a carbocation. I don't think that's possible.
Not possible.
Yeah.
You cannot have ionic mechanism with single-headed curved arrows, because single-headed curved arrows are telling us the story of one single electron going in either direction, which will always be radicals. Either they will create radicals or they will use radicals, but no ions. You cannot have ions if there are radicals. If there are if there are ions, you cannot have radicals. They don't go in the same reaction. They're separate things. Absolutely. So if that were happening, that's not possible. So what should it be?
A radical.
But if you wanted a carbocation, then your arrows need to change. Because that's a double-headed. Those are two electron processes.
And the chloride has a negative charge.
Right, chloride will have a negative charge, absolutely. So guys, there's some things that you need to pay attention to as you are explaining and writing mechanisms for different reactions. Certain fundamental ideas certain rules cannot be violated, because all of these atoms are following the octet rule. Covalent bonds are made of 2 electrons. Those rules are the same. Are we good, everybody? Any questions? Okay. So let's continue with the chapter. We have finished SN2, SN1. Now we are going to look at another layer. We're going to add another layer to it. So far we saw, excuse me, let me take an example. So far we have seen how a leaving group, substrate with a leaving group, nucleophile, right? We've seen how the nucleophile, which is electron rich, can attack the electrophilic carbon, which is electron poor. I'm not showing the mechanism, I'm just showing how the electrons are moving here. Of course, it could either be SN1 or SN2, depending on substrate, nucleophile, all of that fun stuff. But the point is that this is going to result in what kind of reaction?
Substitution.
Substitution. Isn't that right?
Yep.
Okay. How about same substrate, same electron-rich entity, but this time it's doing something different. So that's going to be our next focus. The carbon that has the leaving group attached to is labeled alpha. We are looking at the beta carbon, meaning the carbon one away from where the leaving group is, beta. You good, everybody? So another thing hydroxide can do, what are two things, something that's electron rich, they can do two things. They can behave as two things. What are those two things electron rich things stuff can behave as?
Acid or base?
Not acid or can
No.
Oh, sorry, I heard.
Base and nucleophile?
Is that what you said? Yeah, I missed it. Nucleophile and a base.
That's what I meant.
Here it's behaving as a nucleophile, but it can also behave as a base. Meaning, what does a base do? Takes a proton from the beta carbon. This is not a mechanism again, I'm just showing you the electron flow. If it takes a proton, so this is acting as a base and that was acting as a nucleophile. So as a base, it can take a beta hydrogen. What happens to, and please notice those are double-headed curved arrows because these are two electron processes. So where do those two electrons go?
It goes to the carbon.
Go here. Can carbon ever make 5 bonds?
No.
So that gets out. What's the outcome? What is that? Sorry, go ahead. What does that create?
A pi bond.
And what else? What? The byproduct. Is that right? Everybody? Yeah? What kind of reaction is that? So the first was substitution, nucleophilic substitution. What is this?
Elimination.
Elimination reaction. Nucleophilic substitution and elimination reactions go hand in hand. because the idea is anything that's electron rich can either act as a nucleophile, do substitution, but hey, it can also act as a base and do elimination. So that's that added layer that if you're doing substitution, there's probably going to be elimination as well. And vice versa, if you're doing elimination, there's probably going to be some substitution as well. But we will put it all together a little bit later. Let's first just look at elimination reactions. And just like substitution reaction has two mechanisms, SN1, SN2, elimination reaction also has two mechanisms, E1 and E2. I'm going to do E2 first, then E1, and once we've looked at both of them, then we put all four of them together and do a comparison of, so how do you predict what is going to be the major product or minor products and so on and so forth. Does that sound okay, everybody? So first we focus only on E1. Excuse me, I misspoke. E2. And then E1, and then we'll put all four of them together. Okay, so can somebody tell me what SN2 stands for?
Nucleophilic substitution dimolecular.
Bimolecular.
Bimolecular.
You're absolutely right. So what do you think E2 stands for? E is?
Elimination.
And 2 is?
Bimolecular.
Exactly. And why bimolecular? Why was SN2 bimolecular? What was the reason we called it bimolecular? And what are those two things that affect the rate?
Substrate and base.
So what do you, nucleophile.
Nucleophile.
So what do you think, why are we calling this bimolecular? Because the rate depends on two things. What are the two things the rate will depend on in this case? What are the two things involved in this reaction? Base and
Substrate.
Exactly. Same reason. SN2, I'm trying to draw a parallel between the two, guys. In SN2, what kind of mechanism was that? Was that concerted or step by step?
Concerted.
This is also concerted. That is why it's bimolecular. That is why both substrate and base are going to affect, because everything is happening at the same time. You guys with me? Okay. I'm going to take the same example to illustrate the mechanism E2. We'll do it a few times, we'll write it a few times, but let's start with the same example, which is, what do I have there? Cr. So plus sodium hydroxide, and generally speaking, elimination requires heat. So, or rather I should say, if you heat the reaction, elimination is generally favored over substitution. So that's going to be kind of a hint for you. If I'm showing that heat, oh, maybe she's pointing me in the direction of elimination. That's what she wants me to focus on. So take that as a hint. Everybody okay? Can someone tell me what will be the product? So once again, it's the beta carbon. So that's alpha, beta, on either direction, of course, if they're different. Loses a hydrogen, proton to the base. So the base takes a proton from there, beta, creates a pi bond, kicks out the leaving group. You guys following that? Is there going to be an intermediate? If it's a concerted reaction mechanism, should there be an intermediate?
Transition state.
So therefore we draw the transition state. Because there is no intermediate for us to explain, we draw the transition state. Okay, let's try and draw the transition state for this one. Again, the carbon-chlorine bond is breaking, right?
Yep.
The carbon-hydrogen bond on the beta position is breaking. Which bonds are forming? The oxygen-hydrogen, right? And what other bond is forming? The double bond is forming. The pi bond is starting to form as well. The electrons, again, you got to balance it out. You good, everybody? Charges. Where? What?
Partial negative on the hydroxide.
Just a second. Let me put that sign there. Yes. Yes. What were you saying? Partial negative on the hydroxide. Let's be more specific. Which atom?
Oxygen.
And where else? What else? Charge. Chlorine what?
partial negative.
Good. What else?
The hydrogen that's connected towards the hydroxide, that would be partial positive.
You mean this one?
The
This
one on
one?
the left.
That one?
Yeah.
So let's process. Let's think about it. It's losing electrons here, right? Because those electrons are going away. Am I right?
Mm-hmm.
But isn't it getting electrons here?
Mm-hmm.
So if I'm losing there, but I'm getting here,
Neutral.
I'm the same. Make sense, everybody? What about this carbon, the alpha carbon? It's losing, but then it's getting
Mm-hmm.
Neutral.
neutral.
Wouldn't it be neutral then?
Yes, exactly. Neutral. Exactly. So should there be other charges in here? Not really. And when that goes through, what chloride has gone, become full negative, gone. This has become an alkene, right?
Mm-hmm.
And that has become
Water.
Water. What?
elimination product. You guys with me, everybody?
Mm-hmm.
That is E2. Notice how similar SN2 and E2 are. And it's really about where this guy is going. If it's taking a proton, it's going here. If it decided, no, I'm going to go there, then you get substitution. Because so that is why SN2 and E2 go hand in hand. Yes?
So the only difference is the alpha and beta carbons and heat.
Say that again.
So the differences between E2 and SN2 is the heat.
The difference is the outcome of the product. Now, which one is being preferred, we'll get to that part later. Right now, I want us to just understand E2. Because we already know what SN2 is. Let's understand E2 really well before we compare the two and say, okay, which one do you think will happen here or there? And so on. Then we'll get to that later. Is that the question you're asking, Carrie? Right? So right now, I just want us to focus on E2. Let's understand it inside out before we do a comparison. Is that okay? But what I did say though earlier was, in reactions, if I mention heat, that's a hint from me to you that I want you to think about elimination instead of substitution. That's kind of a hint I sometimes give in exams and quizzes. Okay, go in this direction. Now you want to go in that direction. But we'll talk about all of that later. Okay? But do we understand the mechanism, guys? Yes? Cool. Let's try it one more time. So, does it, okay. So I'm asking you to think elimination right now, not substitution at the moment. So, product or products, sometimes multiple are possible, we'll get to that part in a bit. What would be the product?
Same alkane, but with OCH free. No.
Alkane.
Alkene.
Where is the double bond?
Okay.
So, here's how you process it. Where's the alpha carbon? That's the one the leaving group is attached to, right? But where is the proton going from? It's going from one of the adjacent carbons. Isn't that right? Those are the betas. Does this one have any hydrogen?
No, it doesn't.
So can it make a double bond there?
No, it
No.
can't.
Does that have hydrogen?
Yes.
Can it make a double bond
Yes.
here?
Yep.
So what's your product? In this case, only one. Isn't that right? And what else? Byproducts.
NABR plus OCH free minus.
Why OCH3 minus?
Because it broke.
But will it be minus?
Methanol.
Let's process it. Maybe
OCH free
when we
OH,
write-
okay.
When we write the mechanism, maybe we can go back and change that. So what's the mechanism here? First of all, E2. This is E2. We're only thinking E2 right now. So everything is happening in one single step. Isn't that right? What's the base? This time notice there's no nucleophile, we're talking about base now because there's a proton acid-base reaction happening. So what's the base here? OCH3 minus. It's the methoxide ion. It takes, it's electron rich. Same reason why it was a nucleophile, it's the same reason why it's now a base, takes a proton from the beta position. This is the alpha. This is always the alpha carbon. So it's more of a reference point for us. And if it takes that proton, this carbon-hydrogen bond breaks and we make a pi bond, which means that we need to kick out the leaving group. Let's draw the transition state. Since it's a concerted reaction, we should draw transition states for all concerted reactions.
Quick question.
Yes, please.
The CH3O minus, shouldn't that have an H attached, or am I misunderstanding?
Yeah, we're going to come back to it.
Okay.
You're absolutely right. Someone said that is the answer. Then let's figure out and see if that should be correct.
All right.
Absolutely. So this bond is breaking. This bond is forming. This bond is also forming. This bond is breaking. What's the charges and where?
Partial negatives on the oxygen for the OCH free and the bromide.
Good. And then when it goes through, what is left behind? Well, that becomes the product. Br becomes Br minus. So what does OCH3 become?
CH3OH.
It won't stay that because it's taking a proton, which should become neutral. That's E2. Everybody okay? Yes? Questions? Okay, then this is what I want you to do next then. If you understand what's going on there. Okay, 2-bromobutane. Please, can you go ahead and draw 2-bromobutane? 2-bromobutane. Excuse me. You guys with me?
Mm-hmm.
So what is 2-bromobutane?
Butane with a bromide on carbon 2.
And if this is heated with sodium ethoxide, product or products? Please, go ahead. Let's figure this out. 2 minutes. Product or products? Done? How many different beta carbons there are? It shouldn't take us this long, guys. How many different beta carbons are there?
2.
So then how many products?
2 products.
Can this lose a proton?
Yep.
Then you'll get a pi bond there, right?
Yep.
Can this lose a proton?
Yep.
That's beta as well. So then you'll get a pi bond there. So what are the 2 products?
Double bond on carbon 1 and a double
Isn't that
bond
right?
on carbon 2.
Can there be one more? E2.
The primary one?
That's
The resonance with, or no?
There's no resonance. There's no carbocation.
No.
If there were a carbocation, you can think about all. This is E2. Conservative more as carbocation.
So in the third one, we can't put anything there.
That's too far away.
That's too far. Okay.
Alpha, beta.
That's it.
That's it.
Okay. Yeah.
Not gamma. I'm not going beyond. Can there be one more? What is she talking about? There's no stereo center, but can there be a stereoisomer?
Yep.
What would that be?
1.
There's no stereo center, you're right, but do all stereoisomers require a stereo center?
No.
Which ones don't?
Wait, why is there not a stereo center?
I'm not talking about the reactant, I'm talking about the products.
Oh, okay.
Product.
Okay.
Guys, one more. Product. Is it possible to have stereoisomers without having stereocenters? The answer is heck yes.
Yep, yep.
What is she talking about?
Diastereomers.
Somebody said something?
Diastereomers.
Okay, so which one of these can have a diastereomer and what does that look like?
The one on the left, it could have two different
This one?
H's.
It's the third
So,
carbon.
so,
You can have one coming forward and one coming back.
ooh. Okay. Please go ahead, grab a box of models, everybody. One, oh, come on.
Thank you, Dad.
That's the fun one.
A box per
One
table.
box,
Yay.
please. One box per table at least. Please. And I want you to make this for me. And tell me if you can.
Here.
Is this what you meant, Josh? Is that what
Not
you were
really,
trying-
but
Oh,
yeah, I guess that works.
okay. I want you guys to make this for me and show it to me, please, everybody.
A butane. A butene. A butene.
Please, quickly.
Butene.
It's a 2-minute job, guys. Let's not take 20.
Wait, isn't this the?
Just take 4. And how do we make
Isn't
a?
this the-
Did we talk about how to make a double bond?
But this one?
Oh no. Yes, exactly. Use the gray ones for sp2 hybridized. So guys, if you're making a double bond, take one of these pieces right here, the gray double bond with the gray piece. So if it clicks on there, and one more.
One more one.
This one, I was just, and then clicks on here, that's a double bond, right? So use one of those pieces, and then, yep, exactly. So take this and click it. You can hear that click sound.
So then we get the black ones? Or? So,
Got it? Got it? Why gave up? I was not giving up there. Let's see. Yeah, you can do that.
A butene.
Take one more, put it on the other side, and then attach them to something else.
A butene.
wouldn't it be like
Got
this?
it? Everybody got it? Can you make it look like that drawing? Perfect. Can you make it look like that drawing that I have on the board?
2, 3.
Can you?
Yep.
Can you?
Yep.
No, you can. Right?
No, you can't.
Hopefully you can't, because if you could, I'm like, oh shoot, what's going on here? Why can we not? What's the hybridization of these two carbons?
And
And
sp2.
if they're sp2, what should be the shape? They both have to be trigonal planar. If they're both trigonal planar, then all the 4 things coming off the double bond have to be in the same plane. So you can either draw it like that. Sure, you can do that. You're holding the double bond perpendicular to the board, or you have to have it this way. You cannot twist that double bond where 2 of them are perpendicular to the board while the other 2 are in the plane of the board. That's not possible. This is not possible for alkenes. Have you guys proved that to yourselves?
Yeah.
Everybody okay? Okay, cool. So let's go back to the original question. Can one of them have a stereoisomer? Can I erase this part, guys?
Yes.
Okay. So please, think about it. What's the shape? What's the hybridization? What's the shape supposed to be? Because I'm still getting this, guys, and I need you to try and break that habit. It's a bad habit to have. Now,
Oh,
Okay, I get what you're trying to say, but that's not possible. Why is that not possible? Those have to be linear. sp hybridized atoms have to be drawn linear because that's what the shape is. So please, let's break these bad habits. Anyways, coming back to the original point, can one of these have a stereoisomer? I wouldn't ask if the answer weren't yes.
Maybe the second one can be this or this.
What is this or this?
I don't, like, maybe wrong, but.
You
one,
do
two,
know
three,
it. That's
four.
what I'm asking. You do know it.
Cis and trans.
There you go.
Cis and
This
trans.
or this sounds so much.
Oh, there
And
you
are
go.
they stereoisomers? Yes, they are. What kind of stereoisomers are they?
Oh,
What kind of stereoisomers are they?
Cis and trans.
Okay,
How does that-
which category do they fall under? Enantiomers or diastereomers? They're guys, this is taking us back to chapter 5 last
Diastereomers.
quarter, which I've said already. We can't forget what we've already learned. These are diastereomers. These are geometric isomers, which is a subcategory of diastereomers. Absolutely. So what's the total number of products here? Organic, we don't care about the byproducts. What's the total number of organic products? 3. Is there going to be one major minor? Yes. So here is the rule. The more stable alkene is the major product.
oh,
And this rule is called, memorize this name because it's going to come up a lot. Zaitsev's rule. When elimination happens and you're
Ouch.
creating an alkene, then the more stable alkene is the major product. That's called Zaitsev's rule.
oh.
So, what is the order of stability of alkenes? The idea here is the more R's on the carbon-carbon double bond, the more stable it is. The more stable the alkene is, the major product that is. That's called Zaitsev's rule. Are you guys with me?
Mm-hmm.
So, the more R's, what does that mean?
R groups mean organic groups.
So, this is an unsubstituted alkene. There is no R on it, it's unsubstituted. Agreed?
Mm-hmm.
This is the least stable alkene because there are no R's on the double bond. Then comes the mono-substituted alkene. What does mono mean?
Only one.
And substituted group on the alkene. 1R mono-substituted alkene is more stable than the unsubstituted. Are you guys with me?
Mm-hmm.
Then comes what? What do you think?
Dye substituted?
Good. Now there are 3 kinds of dye substituted, right? Because there are 3 possibilities for the groups to be on the double bond. Of the 3, oh shoot, I forgot. I'm trying to remember. I know what 3 they are, but I'm trying one of them.
2 R's.
I think that is most substituted. Okay, so of the 3 kinds of dye-substituted alkenes, this is called geminal dye-substituted alkene. I will write these terms in just a minute. Geminal because both R's are on the same carbon. Then comes trans but this is trans, but it's not geminal, it's called vicinal. Vicinal means on adjacent atoms. Geminal is if 2 things are on the same carbon, those are called geminal. If the 2 things are on adjacent carbons, they are called vicinal. So the 2 R's are on adjacent carbons, so those are vicinal. Trans because those are opposite each other.
Can they
Oh, sorry, I made a mistake. Sorry. No, it has to be cis, not trans.
Cis-benzene.
Cis is less stable than trans. Sorry, what were you saying, Mark?
That.
That one, yeah,
Yeah.
absolutely. I don't know, I don't even know why I wrote that. And then, of course, trans-vicinal is more stable than cis. So those are the 3 di-substituted alkenes. Then comes the tri-substituted alkene. And the most stable alkene is a tetra-substituted alkene. Is the most stable of all. So, unsubstituted, least stable. Mono-substituted, 1R. Next. Then there are 3 di-substituted alkenes, then tri, then tetra-substituted. You guys with me? So of that, can you tell me which would be the major product in this example?
Which would be the what?
Which will be the major product?
Product 2.
Zaitsev's product. Zaitsev's product is the
Zaitsev.
more stable alkene. The more stable the product is, the more it will be produced because the activation energy for its formation is smaller. You guys with me, everybody?
Mm-hmm.
Okay. Questions so far? Can you write the mechanism? Since we are trying to get in the habit of writing mechanism, go ahead, take a couple of minutes, all of you, write out the mechanism, how this reactant becomes the major product, only the major product. Can I erase this?
Do we have names for those?
Well, unsubstituted,
Oh, okay.
mono-substituted, di-substituted, because there are 2. So what would you call this?
Tri-substituted
Tri-substituted, right?
and tetra.
2, 3, 4, tetra-substituted. Okay? Yes, please go ahead, take a couple of minutes, write, because as I've said already many times, the more times you write it, the more times you actually put pen to paper, the better you are going to remember it, and you'll start seeing the patterns that hopefully very soon we will start recognizing. Not there yet, but hopefully soon. Okay, are you guys with me? Everybody?
Yep.
Okay, now I want you to, let me see. I'm trying to think of something, give me a second. Okay, let's do this. So that is regioselectivity, Zaitsev's rule. The more stable alkene is the major product, that's regioselectivity decided by Zaitsev's rule. Go ahead, make this model for me. I think I stole this from you guys. Please.
RNS.
So the regioselectivity of E2 or
1, 2,
elimination
3,
is
4,
decided by
5.
Zaitsev's rule, which says the more stable alkene is the major alkene. Great. What about stereoselectivity? By the way, does anybody remember the stereoselectivity for SN2? What is the stereochemical outcome for SN2?
Opposite.
What is that? What's
More
the word
stable.
we use for that? Louder? Inversion, right?
Inversion
Because the
is
nucleophile has to come from the opposite side of the leaving group, there'll always be inversion of stereocenter. Is that right?
Mhm.
E2 is also highly stereospecific. And I'll write the rule in just a minute because you guys are busy making that. Do you guys all have it? Everyone? Very quickly, guys. Very quickly. Make it look exactly like the drawing. Okay?
To be reacted with whatever. Oh,
Everybody okay?
I thought. Never mind.
Okay. Question. Once you have that, how many products will I get if this is heated with sodium hydroxide? I mean, again, as I've said before, if I'm saying heat, I'm trying for us to focus on
I got it.
not
Okay.
thinking about substitution at the moment. How many
Oh, that's right.
products
Because
will
you're
I
PPRs,
get?
yeah. Never. What?
How many products will I get?
Oh.
Please. 1 or 2 or 3. You missed the methyl group. Where's the methyl? I might suggest you actually put something there, even if you don't make a methyl, but at least put something so you don't forget that there's something, because that's going to be
I
important.
made a green one, the methyl
Fine,
group.
that's okay. Something's there. How many products, guys?
Um,
Why 2? Why not 3? So what? So do you all agree that this is one of the products, right? Which we can all write mechanisms for if one of these protons is taken. Everybody with me? Everybody okay? What's the other product? Right?
Mm-hmm.
Is that right?
I think so.
Really? Nobody is
No.
going to say no.
no,
That can't
1, 2,
be.
3, 4.
because
So,
it can't be
Oh,
vinyl.
oh, yeah, yeah, yeah.
Trigonal planar.
what do you mean it
Yeah,
can't
no, you
be?
need to have.
It can't be front.
So if I see that drawing from now on, can I make 10 exclamation points after that? Or maybe 5 question marks? How do you do that? Do you guys see that?
Mm-hmm.
Is everybody following?
Mm-hmm.
If that's supposed to be trigonal planar, can this be in the plane but that be pointed towards you? That's
No.
a 90-degree angle.
Mhm.
That's not 120.
Okay.
Let's draw what we want to show. Is this geometry possible?
No.
If you can make a model for me and show it to me that, yeah, I got it, I will stop teaching. No, okay. The
That's
point is we can't, right? It's a trigonal planar carbon. So what should I change? What should I fix here?
Just a regular.
You gotta keep that geometry in mind. Is there one more possible? Can't it also be this? Yes? Everybody? Yeah?
No, because you're adding on an additional carbon.
No, I didn't.
Oh.
That is, one of them is cis, the other is trans. We of course don't know that part yet because we'll cover that in the next chapter. But they're stereoisomers of they're diastereomers,
Diaster.
cis and trans, geometric isomers of each other.
Mm-hmm.
Agree?
Okay. Yep.
Everybody okay?
How do you get
Yep.
the last one?
Say again?
How do you get the last one?
See?
You have to break the
just have
bond.
You'll have, because you are breaking that one. You are breaking this bond and then reforming, breaking. Maybe in that process it twisted. Didn't we make cis and trans there? Right? I love that expression on your face, Camilla, because that's a great expression. That's the thing we want to elaborate on. So hold on to that expression, that thought, that nagging thing in your head, like what's going on? That doesn't make sense. Hold on to it. Hold on, that's a good one. But 3 possible written on the board, agreed?
Yep.
Now, for the moment, which of these 3 do you think is the least major? Will be totally minor, without a doubt. Do you guys agree? Right?
Yep.
It's mono-substituted, so it's the least stable of all 3. Isn't that right? Everybody okay?
Mm-hmm.
So for the moment, can I just take this out of our focus? We're not concerned about that at the moment. Let's focus on those. What's the difference between those 2 products? They are stereoisomers. They are geometric isomers, diastereomers. So what is the stereochemical selectivity for E2 reactions? Here's the rule for E2 and then we'll elaborate. In E2, the alpha carbon leaving group bond and the beta carbon hydrogen bond. These bonds must be anti-periplanar with respect to each other. Otherwise, E2 cannot happen. If you cannot make that work, E2 cannot happen. For E2 to happen, these two bonds, this bond and this bond, must be anti in the same plane. That means same plane. What does anti mean?
Not.
Okay, come on, let's do better than that.
Against, or
What does anti mean? Opposite, meaning what
Opposite.
is the dihedral angle supposed to be? What is the dihedral angle? What should the dihedral angle be if two things are going to be opposite?
120.
Ooh,
No.
opposite. 180.
180 degrees completely.
Anti, guys, we've done this last quarter again. Conformers, you've got anti-staggered, you've got gauche staggered and eclipse and all of that. Do you guys remember?
Mm-hmm.
Anti, whenever two things are anti, they are at 180 degrees from each other. Isn't that right?
Mm-hmm.
In the same plane. If we cannot achieve this conformation, E2 cannot happen. You guys with me?
Mm-hmm.
Go ahead, pick up your model. The model you made for this reactant. Now what I want you to do is the following. Ready? I want you to look at your model and I want you to look at this bond and draw for me the Newman projection. You guys remember Newman projections?
Which way do you want to look at it from?
That's a great question. Which way should I? Doesn't matter, right?
Uh-huh.
You can either put your eye right there and look, or you can put your eye right there and look. Which one do you prefer? Okay, let's do one thing so we're all the same.
The left.
Which one do you prefer?
left.
2 to 3.
So here,
Yes.
you want to look down this direction?
Yep.
Okay, so let's go ahead. Let's draw the
Newman.
Newman projection. So this is our front carbon. Isn't that right?
Yep.
And then we have the back carbon. Okay, let's focus on the front carbon. If you're looking in that direction, which direction is the methyl in?
Down.
Bottom.
What about the Br?
Right.
And what's on the left?
And H.
You guys agree with the front carbon?
Mm-hmm.
What about the back carbon now? What's pointed up?
Ethyl.
Do you all agree?
Yes.
What's pointed on the same side as the Br?
The methyl.
Do you all agree?
Mm-hmm.
Everybody okay? What's on the same side as this hydrogen?
Hydrogen.
Another hydrogen.
Okay, cool. Now let's isolate the alpha C leaving group bond. Where is that bond? That's this bond right here. Isn't that right?
Yep.
Agreed? This bond right there. Where is the beta CH? Where is this bond?
It's
Down.
right there.
Mm-hmm.
What is
Opposite.
the angle between these two?
180.
180
So
degrees.
therefore, if the geometry of the molecule can achieve that, E2 can happen. Will happen. Okay, cool. So now, will we actually get both products that are on the board, the cis and trans, or just one? In this case, just one. Which one? So let's figure that out. So when elimination has taken place, right, the base hydroxide comes in, takes the proton, the beta hydrogen, this bond breaks, isn't that right? And makes a double bond, and that bond breaks and bromide is kicked out, isn't that right?
Yep.
I'm going to keep everything else the same. I'm just getting rid of what's leaving. Nothing else I'm going to change. That's gone. This is gone. So what remains? I have that I have hydrogen here, I have ethyl here, and I have methyl here. Agreed? Everybody?
Yep.
So can you tell me which of those two drawings matches this product?
Let's see.
Your double bond is here. Between the front and the back carbon is where the double bond is, which of course we can't see because we're looking right through it.
The
So
first-
which of those
the
two
first-
drawings?
The first product,
Because
H and ethyl are on the same side.
on the same side. Do you guys see that?
Yep.
And methyl and methyl on the same side of the double bond. This product is not possible in this example. It's not even possible. It's not like it's a minor product, it's an impossible product, because in order to create that product, you have to rotate the bond, and as soon as you rotate the bond, you won't have that anti-periplanar geometry anymore. You cannot do it. Are you guys following this discussion? Yeah?
Yep.
Everybody? Okay, so let's analyze more. Let's go ahead, let's try this one. Actually, wait. Sorry, give me a second. How many of you understood that? How many of you did not? No, see, at least the did not people are braver than the yes people. Okay, the yes people, how many of you got it? Please get up and go explain to the ones who didn't get it. Give me 5 minutes, 10 minutes. 5 minutes, I'll be right with you.
Did you? Yes. Are you yes?
I think I get it.
All right.
Yeah,
I think I got it.
So what
just right there. Like,
You're struggling with that part there?
yeah, like when it, what did you say? Like,
Okay.
HO, what happens?
So they have to be 180 degrees apart.
Uh-huh.
So this is the one that's leaving.
It has to be completely opposite.
So you look, follow a straight line.
Okay.
H is on the opposite side. So that's what you're gonna get rid of.
Yeah,
You're getting rid of H also.
This H
Oh.
specifically.
Yeah, the H is completely
You
opposite.
can't get this one because it has to be 180 degrees. This is 180 degrees, so you're going to get rid of this one. The OH bonds to the H, so it takes this H.
Oh,
The
okay.
H takes this electron, takes it here. Basically showing
Which means
it's
that
basically the same thing as
your bromine, you're leaving your beta.
Okay, so, and the one in the middle is the only one that matches.
So when you take them out, your major product
it's the
is
same
gonna be
thing as
So does
this.
that mean
the
that's
flat version.
Oh yeah.
Which is
Yeah, that's
not
right.
so your major product
Oh, okay.
cannot have, because you're not moving these around, you're just taking away.
So that's the only one that's.
It's basically saying the same thing as this.
Uh-huh.
So once both these are gone,
I forgot why.
you're left with just these. You really imagine you just erase these.
Okay.
This is what you get.
Got it.
Yeah.
You can see these
Exactly.
Two, you see these two are grouped together. These two are grouped together. So you look here. These two are in a group. These two are in a group.
Yeah.
Two methyls. This is supposed to be CH.
The methyls. The methyls
Perfect.
are
Thank
the
you.
methyls
Yeah.
are in the same area, and so is the
Yeah, I
hydrogen and the
just-
ethyl.
Yeah, it was, I guess I spaced out in this part when it went from HO to that. But then from there to there I understood because I could see it. But yeah, thank you.
Okay.
Got it? Okay, kinda. We're going to do more examples. See if it solidifies. Vincent?
So is that, so the one in the middle is
Yes.
the only possible product?
Of these two. No, that is minor.
But that's.
So
but
this
that's
is
the-
not possible.
Okay.
Not possible. You'll get two.
That's just least stable.
That's the less stable alkene, so it's minor. This is the major because it's a more stable alkene. The other one is not possible because of that. Does that make sense? Everybody? Everyone okay? And why is the other one not possible? The one that I erased is because in order to make that, you have to rotate this bond, which is my next example. But as soon as you rotate the bond, then this and that, they are not anti anymore. And if they're not anti anymore, E2 cannot.
And
You guys with me?
So it would be, it should be where that CH2 is.
Yes, exactly. Which means then they're not 180 degrees away from each other. So then there's no E2. So let's try this out again in a different example and see if this starts to solidify. So I would like for you to draw, and all of you work together. You help each other out here. And I hope I am naming it correctly. I think I am. 3R, I know. 4S. 4 bromo. 2, 2, 3 trimethyl hexane. Okay? And then the question is, show the major product if this is heated with sodium ethoxide. Right? Again, we are focusing on E2 right now. So that's what we are thinking about. So if you see a question such as this, what's the first thing you would want to do? Draw it. Exactly. Draw that and keep the stereochemistry in mind. So go ahead, let's draw it first. Can I erase this board or should I leave it here for comparison purposes or anything like that? Leave it? Okay,
yeah,
cool.
leave it to
I
compare.
want to not erase this yet either. Okay, we have plenty of space.
2.
So first is let's draw it.
3R4S.
Making sure that your stereo centers are correct.
And bromine. And this is an H. So 1, 2, 1, 2, 3, 4. 1, 2, 3, S. Yep. Methyl. One,
2, 2,
2,
2, 3.
4. 1. Shh. H has gotta be on a wedge.
Does anybody have?
1, 2.
Does anybody have the structure drawn for the reactant? Not the product, just the reactant. Almost.
R.
I'm just counting.
No, that's okay.
1, 4, 4.
Hexane.
So the first step is your stereochemistries have to be right, assuming
Two.
that I did them right.
3. If it's on a wedge, you change it, right?
Yes, if it's on a wedge, you invert it. If 4 is on a wedge, you invert it.
So to the left is no. So R3.
Major product.
Right, so no. So this is I think I got it.
I just remember because when you go in, you know S, and then R is just like
I think I got it. Oh wait, it's just one bromo, right?
Yeah, 1 bromine.
On 4.
Yeah,
Oh.
bromine on carbon 4.
What am I doing? 1, 2. Oh no, I got it right. 4 bromo. But 3R?
Okay, do we have it? Are you sure?
What's 3R? 1, 2, 3. 4 bromo.
Okay.
3R. I don't
Of
know.
course, I mean, depending on the orientation of your molecule may be slightly different.
Oh, okay, yeah, this is methyl. Okay, okay.
Maybe
Duh.
slightly.
Okay.
Not possible. It's wrong. It's trimethyl. And product, we'll get there. We are not there, but Some of you have drawn this. Oh shoot, I forgot. But okay,
I
some
won't say
of you
this
have
is
drawn
small.
this.
I don't know.
Tell me 1, 2, 3,
I'm not sure
4,
what to do.
5, 6. Is this the one on a dash?
Yeah.
Yeah, that's the one on a
That's
dash.
the wedge.
Methyl's on a dash and
I mean,
bromide's on a
that's
wedge.
one way of drawing it. I mean, I could have drawn it flipped here or flipped there as long as you got 3R, 4S. That's what happens. Everybody okay? Okay. Now, I need you to, for us to figure out in this question, starting here, we need to figure out the major product. So here's what I suggest you do. This is how our thought process is working. First step is this. Next step is regioisomer. How many regioisomeric elimination products can it make? Regioisomer, meaning how many beta carbons are there? How many beta carbons does this compound have?
2 beta carbon?
Do you all agree? There is one on this side, isn't that right? Because this is alpha. Does that have hydrogen on it? Can
Yep.
it do elimination?
Yep.
Yes, no, maybe.
Um,
Yes, what's the product? If it does elimination here, what's that product?
double bond between carbons
So
4 and
the
5.
blue product, that doesn't change, right? Agreed?
Mhm.
What about the other beta carbon? Does that beta, I'm going to make that red, does that have a hydrogen on it? Can it therefore do elimination?
Yep.
Now, so then what's the product? If that one is doing elimination, what's the product? Well, one option is this, isn't that right?
Mhm.
Is there another option? Or isn't that right?
Yeah.
Of course, we have to figure out which of these two in a bit, but there are two possible stereoisomers possible there. Agreed?
Yep.
Of the three, which will not be major? So we can at least just take it and stop thinking about it. Do you all agree that of the three, this is the least major? Because
Yep.
it's di-substituted, whereas these are tri-substituted. Agreed?
Yep.
These are the ZSEF's products. That's not. Yes? Cool. So can I just stop thinking about that for now?
Yep.
Let's focus here and decide which one. Because only one is possible, of these two is possible. So the idea again is, the rule again is that the C leaving group and the beta CH bond must be anti-periplanar to each other. Where is the hydrogen oriented on the red carbon?
Oh,
Towards us.
it's on a
Let me
wedge.
draw it again, please. Isn't that right?
Yep.
Do you think the angle between this bond and this bond is 180 degrees?
No.
They're not. They have to be opposite. So what do I need to do to make them become 180 degrees? I need to rotate it. I need to rotate about this bond. Isn't that right? Now,
Yeah.
here are the options here, guys. This is all a personal preference thing. Some of us, like me, I like Newman projections. I work better like this. I can see things better. Some people are great with just closing their eyes and doing it in their head and seeing it. It really depends on what. You might want to make models and see it. Okay, what if I rotate it? Does it work and so on? Those are all personal preferences. You guys with me?
Mm-hmm.
Yes? So can I just do Newman projection? Because that I can see things better that way.
Yep.
So Newman projection, we are going to draw Newman projection along that bond right there. And this time I'm going to look at it from this side. Is that okay with you all? Yes. Okay, so what am I seeing? Can I go here, please? Yes. So I'm seeing the front carbon, back carbon. Front carbon, I'm seeing the T-butyl group is on the front, top. And then I'm seeing a hydrogen here, and I'm seeing the methyl here. Okay? The back carbon, I'm seeing ethyl come down here, and I'm seeing Br there, and I'm seeing hydrogen here. Okay? Now, which two bonds are we interested in? Which two bonds need to be anti-periplanar?
The 180.
Which two? Which two bonds
The
need to be
bromine and the
180?
bromine and the hydrogen.
This bond right here and
That hydrogen.
this bond right there. Right now they are not 180 degrees.
Oh.
So let's rotate. If I rotate this, and again, as we've discussed earlier, it doesn't matter which direction you rotate, it doesn't matter which carbon you keep still and which one you move, as long as we achieve the goal. So I am just choosing to, it's a total choice here that I'm going to keep my front carbon be still. You could have chosen the other way, that's totally okay. And I'm going to move my back carbon. So where do we want the BR? We want it opposite this, right? This is where we want BR, isn't that right?
Yep.
So if I move BR here, hydrogen goes there and ethyl goes here. Agreed?
Yep.
Are they now situated in the right arrangement?
Yep.
Now they can undergo at E2. We need this geometry for E2 to happen, otherwise E2 cannot happen. So this cannot do E2, but once it rotates, gets into the required conformation, now E2 can happen. Are you guys with me so far?
Yeah.
So can I just take a shortcut? This is really a shortcut. This is gone, this is gone. Agreed?
Mm-hmm.
What's left?
That.
So what is the orientation of the T-butyl and ethyl?
They're on the
They're the
same.
same side of the double bond, right?
Mm-hmm.
Same side of the double bond. And methyl and hydrogen are on the same side of the double bond. Do you guys all see that?
Mm-hmm.
So which of the two stereoisomers will be created and which one is not possible? And that one, not possible. This is your major product. Are you guys following the thought process here? Everybody? Yes? So the idea is, in order for E2 to happen, the carbon leaving group bond and the beta carbon hydrogen bond must be anti. Otherwise you can't do elimination. We can't do E2. Sorry, can't do E2. Are you guys with me? Yeah? Okay, same thing. Let's do the next one then. Let's see which one. Cis. Cis 1-bromo 2-methyl cyclohexane. Cis 1-bromo 2-methyl cyclohexane. If this is undergoing elimination heat, E2, when we heating it with sodium methoxide, how many products? And which one will be major? You guys with me? Now for such questions where it's a cyclohexane compound, what's the most stable form of cyclohexane, people? Chair. Think that. Think chair. Okay, this is cis 1-bromo 2-methyl cyclohexane. So if I put bromine equatorial, methyl will have to be what?
Equatorial.
Axial.
Axial.
Oh, axle. Okay.
Guys, can you do this quickly? Make this quickly. And everybody doesn't have to have one. Maybe there's one per table or two per table, but let's do it very quickly. Because I want you to see
I'll get this
something. That's the detail. Do you agree that that is cis and it's the stable form?
You can start from.
Because the bigger group, bromine, is in the equatorial position. The smaller methyl is axial. Remember, the equatorial position is more stable because there's more space.
You're going to do one, right? I mean, let's just do it.
Once you have that,
You can start building it and I'll do this.
I'll start building it.
everybody got it? put the
Five.
bromine, use
I don't know
one
if you need-
color for Br, one color for methyl, so you know which is methyl, which is Br, so on and so forth. Make sure that bromine is equatorial because it's more stable to be there because bromine is bigger than methyl is. Needs more space. You guys got it? Now here's the question I have.
Got it. One bromo, two methyl.
Where was I?
Oh,
Yes. Question I have. Guys have it?
Yes.
Can you tell me, in this structure, is there any hydrogen on beta to this, on the beta carbon that's anti to this bond? On any sides? If you
No.
look at a beta carbon, is there a hydrogen that is anti with respect to that?
No.
I don't think so. Maybe.
No, it's, oh wait, you need to have these down, don't you? Or no? Or how?
No? None.
Oh, is
Agree?
it that like that?
Yes.
180 degrees it has to be. Is there any hydrogen? Is this 180 degrees with that?
No.
No. Does that have hydrogens?
It.
This
do-
beta carbon have hydrogens?
yes.
How many? 2?
Mhm.
Is this 180 degrees with respect to that?
No.
Is this 180 degrees with respect to that? Is it? Look at it. Look at the model. If you can.
Oh,
show it to
yeah.
me, I
No.
would- Is it?
No.
180 does not mean
No.
160 or 120 or it means 180 degrees. Absolutely opposite. Yes, no, maybe.
No.
No, not possible. Because the bond that is 180 degrees with respect to that is actually the carbon-carbon bond, not a carbon-hydrogen bond. You guys convinced or no?
Yes.
Because it has to be chair. I don't see your cyclohexane. I'm not seeing a cyclohexane there. Anyways, yours is a chair, but it has to be a chair. That's not a chair. So the question is, the big point here is, if you're dealing with cyclohexane systems, can this do E2? Can it do E2?
No.
No. Why? Because it doesn't have that 180 degree arrangement. So what does it do then? Does that mean it doesn't do E2? No, it does. Just not in this form. It cannot do it in this form. So what does it do then?
Not a chair.
Louder?
Not a chair.
Well, it has to be a chair. But how about the other chair? The ring flip.
Oh, right.
Can we take our chair and give it a ring flip?
Yep.
Go ahead, do that. That's not a chair. No way is the chair. Guys, we've done chairs a lot last quarter. Needs to be a chair, not chairish. It has to be a chair.
Axial
Good.
becomes
So when
equatorial
you do a
becomes
ring
axial.
flip,
Oh.
whichever carbon is down goes up. Isn't that right?
Yep.
So let me draw it. So this is down, that will go up. This is up, that will go down. Isn't that right?
Mhm.
So this is my, if I'm going to call it carbon 1, that's carbon 1. Isn't that right?
Yep.
What happens to axial? Oh, say blah, blah, blah. What happens to equatorial?
It becomes
Axial.
axial.
Equatorial becomes axial. What happens to axial?
Equatorial.
Good. So now, if you look at this conformer, let me make, is there, and remember, this is the leaving group bond. Is there a hydrogen on this carbon, which is going to be axial? What's the angle between these two?
180 degrees.
So can there be elimination happen here?
Yep.
Absolutely. But only when the leaving group is axial. So for cyclohexane systems, when you are doing this analysis, draw it so the leaving group is axial. Because if the leaving group is equatorial, it can't do E2. So anyways, we've got to think about this. So let's just put it at axial. You guys with me? Yes? Okay. What about the other beta carbon? Does it have anti-hydrogen? It
Yeah.
has two hydrogens, one's equatorial, the other is axial. Do you think that those two can also do E2?
Yes.
How many products?
2.
What are those two products? What are those two products? Agreed? Everybody agrees?
Yeah.
Which of these is the Zaitsev's product? Which of these is the product Zaitsev's rule will say is the major product? Absolutely. Do you all agree?
Why?
Because it's more substituted,
Okay.
right? So it's more stable, alkene, because here is one R, it's a tri-substituted
And
alkene.
and the double
This is
bond is more near the methyl than it.
That, again, it's not about that it's near the methyl, it's that it's a tri-substituted
Oh.
versus a di-substituted.
A di-substituted double
So
bond.
that's a more stable. You guys with me? Did we understand that?
Yes.
Sure?
No.
Oh, come on. We just said yes.
Processing,
So
processing.
then, what about the trends?
One bromo, two methyl.
What about that?
Is it the same as the one option?
Tell me what? Tell me what? Don't ask me a question. Tell me which one. Which is the option? What will you get? What will you not get?
Well, the methyl would be in the axial position. instead of
There you go. So let's draw it out. Now this time, I'm going to take a shortcut
This is
because
right.
we know, right, that hey, which position should the leaving group be in order for E2 to happen?
Axial.
Axial. So let's just start there. If we're taking a shortcut, I'm just going to put it axial because equatorial it cannot do E2. Everybody okay?
Yep.
So if that is axial going down and we want trans, which direction should the methyl be on carbon 2? Should it be axial or equatorial?
Equatorial. Or no, axial.
Is it equatorial? Is it axial?
Well, it's going down, so it
If this
should
is
be,
going down,
and the other
the
one
other
needs to
should be
go
going
up.
so should it be axial or equatorial?
Axial.
It's not, cis and trans is not about equatorial, equatorial is cis and axial, axial is cis, that's wrong.
It's up and down.
Up and, exactly. Up and up is cis, down is cis, up and down is trans. It's about that part that you got to remember. You're absolutely right. Now, does this beta hydrogen, carbon, is there a hydrogen on it? Does this beta carbon have a hydrogen on it?
Yes.
What's the, what position is that going to be in? Axial or equatorial?
Equatorial.
Now, if this is equatorial, are these 180 degrees from each other?
No.
So can there be elimination there?
No.
No.
Good.
Oh.
What about the other one? That's also beta. It has two hydrogens. One of those hydrogens is equatorial, obviously, but there's one that's axial. What's the angle between these two?
180.
So can they do elimination?
Yep.
So how many products? Is this product possible?
No.
Is that product possible?
Yes,
No.
but we're only
Oh.
an output of one product, right?
Exactly.
It would only output
You're
one
absolutely
product.
right. And which one would that be? The only one product possible in this case is the other one's not possible. Do you guys see why? We need those two bonds to be 180 degrees from each other. They have to have the anti. And these two bonds are not anti.
Mm-hmm.
Is everybody seeing that? Does that make sense? Then I want to ask you a question. If this makes sense, you ready? Oh, come on.
Yeah.
Where's that enthusiasm?
Yep.
There we go. Let me first I have it in my head. Let me first make sure I have it right. Okay. So, here, oops, sorry. Three stereoisomers of 1-chloro-2,6-dimethyl cyclohexane. Three stereoisomers. Let's call this A, let's call this B, let's call this C. Okay. The question is, when E2 happens, when these are heated with a base, E2, one of them makes 0 products, one of them makes 1 product, and one of them gives us 2 products. You got to match which one is capable of giving us no E2 products, which one is capable of producing 1, and which one's capable of producing 2 E2 products. So go ahead, think about it. Give me the answer.
Wedge up, dash down.
And can you explain it?
Yeah.
So let's think about this. Again, the idea is that the leaving group, carbon leaving group bond and the beta carbon hydrogen bond have to be opposite, anti. Otherwise E2 can't happen. So there are no shortcuts. As soon as you start seeing the patterns, you're like, yeah, of course.
Did you say beta and alpha have to be anti? Or
Yeah, alpha and beta have to be anti.
The carbon leaving group bond has to be anti to the beta carbon hydrogen.
oh, okay.
And show what the products are. So which one creates 0 E2, which one creates 1 E2, and which one will make 2 E2 products, and show the products. Draw the products. And yeah, there is a shortcut. If you start recognizing the pattern, there's a shortcut. The reason you can't do because you can't click it in place. How will it have rigidity with the I think this has been used. Oh, that's not locked it. Have to lock it in. Yeah, I think this bond is bad.
Down.
Yeah.
Down.
Which is VR, which is I mean, which is methyl and
The blue is methyl.
okay, so and this is CR?
PR.
Okay, VR. But we wanted axis, which means
So we have CL back here.
now it's axis, right? So are
And then we
these two
have,
antis?
uh,
Are these antis?
yeah.
No. So you can't have
That's
any
okay.
six. And what about here? This is anti, right? So you can have elimination. That's it.
Okay.
Yes. Yeah, you need to flip. Now bond rotation is always allowed without breaking.
So it's, so the key is looking for hydrogens that are 180 degrees to the
Leaving group.
leading group.
Yes, that's really the key. Absolutely.
So you just look at hydrogens that are
Leaving group.
Not that beta. No. Not these hydrogens don't matter. See, this is, where's your leaving group? Is this your leaving group? Let's first make this chair. That's not chair. And put this axia. So first thing, see, if we don't lock this, it won't be, yeah, you have to lock. Did you hear that click? You got to lock. That's why you're not able to, because now they're locked. This one. Okay, so you make it chair. And you're also using grays are not for sp3 carbons, the blacks are sp3.
those only.
There's so many of them. No, I'm just because you won't get the right angle that way. Yeah, that's why I'm not able to get the right angle. Yeah. So see, it says somewhere here it says it's for sp2. So they give you the right angle that way. But anyways, the point is, let's do a quick thing. Okay, here is the So this is axis.
You need
right?
this?
What?
Did you need this?
This carbon,
I found this.
does it have a
No, I didn't.
hydrogen axial opposite?
Okay, so it's this one.
On this carbon, is there a hydrogen that is opposite the VR? Red is VR. This is VR, right? On this next carbon, is there a hydrogen? You're holding it. They're opposite. So you can have each of them and make a double bond there. So what about the other one? Yes, because see, if they're opposite, what's the angle between this line and this line? Exactly. So you can do elimination, which means you can make a double bond there.
So that's one product.
That's one product. But what about the other one? See, this is not chair because you're not using the right pieces.
Oh, okay.
But okay, I'm forcing it right now.
Can I give you this
Let's
one?
do the same. Oh, you have one? Perfect, thank you. Perfect, thank you. Okay, so first of all, which one? White is white the leading group?
Yeah.
Okay, so we want that axia. This is. No, this gray is not. Gray is not. Sorry. Gray is not.
Oh, this is
sp3.
great. How confused.
Yeah, I know, it's very close.
It's dark gray.
Black is sp3. You got it locked. If you're not locking, you won't get it. Okay. Lock. You're saying white is leaving group? So we wanted axial, because in equatorial they can't do elimination. So, no. Okay. Let's look on, here's alpha carbon, isn't that right? Let's look at this beta. This beta. Is there a hydrogen anti to the leaving group? I'm holding the white piece, right? Is there a hydrogen that's 180 degrees from here?
No.
That's a hydrogen.
But that's
No,
not
that's a
hydrogen.
carbon.
That's a methyl.
So is there a hydrogen that's anti with respect
No.
to that? So you can't have E2 there.
It's
It's gauche. Yeah. So we have to have anti. So can it do E2 and make a double bond here? The answer is no, because there's no anti-hydrogen. Are you guys with me? Everybody?
Yeah.
Okay, let's look at the other beta. This is the other beta, alpha beta. Is there a hydrogen on this carbon that is 180 degrees
No.
relative?
No.
So can it do elimination
No.
there?
No.
So can there be any elimination? You
No.
can't have E2 here, you can't. So how many products?
No.
Zero.
Zero products.
So now do it on
Now
the
then
other
change
side.
it. Go ahead, talk amongst yourselves.
So what one
So
had?
B is what? So the middle one is no.
Oh right.
And
Oh.
then
Wait.
So now here is the other one, which is what?
I
That's
I
180.
did C, and C had one product.
This one has one. Look, it's 100. Wait, no. This
But
one is
correct me
180.
if I'm wrong.
This one is 180.
That's fine.
Is that one A?
Huh?
Is that one A?
It's let's see, one behind.
That was.
It's one behind and one in front.
Yeah, one muffled.
So that's A.
One muffled.
That's
Oh, that's
So
A.
A has one product.
Yeah.
Oh.
I did.
We
C has one product,
And then
but I
B
might.
has
I'm wrong.
B has no product.
Oh, B has no.
I'm moving you over.
Is this the one she used? Did you change anything about it?
Yeah, I changed this
Oh, okay.
because it's one in the back
I
now
did make
and one in the front.
mistake which Eric caught in my question.
I can-
It doesn't change any of your work. It just changes the meaning of the answer. Because I said very specifically, one of them makes 0 elimination products, one of them makes 1, the other one makes 2. And that's, so can I just make a very quick change? How about just make one of them,
An apple.
because
Okay.
otherwise, yeah, then they'll be the same if I didn't make that
Apple.
change. Your process is not going to change, your analysis is not going to change, none of that. But now we have, right?
So
Thank you
apple.
for catching that.
Apple has to be pointed up.
Okay, let's see. So this was one in the front and one in the back.
Apple was down.
Oh, we have to put ethyl?
Yeah, apple. And I just drew this one off. Wait, if it's down.
But is it a wedge or a dash? Because we started with something. So did it change or not change? Are you guys ready with the answer?
C
Okay.
gives us one product.
So I heard C gives us one product, is that right? Yes. And B is proper. What about B? 0 products? What about, thank you. C? 3.
Oh, 3, 2.
I was like, what? Because you can't do cis trans in a cyclohexane. Oh, there's not enough.
Is this ethyl?
Twist. Did somebody think cis trans? No. Okay. Yes. Okay. So what are those those products? Of course, this doesn't give any. Is everybody okay with that? Questions, confusions? The idea is that there are no hydrogens that are situated right. And there is a shortcut, guys. There's actually a shortcut which takes away all the need to make models, draw structures. What is that, a dash or a wedge?
A
Dash.
dash.
So what do you want this hydrogen to be? To be opposite.
It has to be on a dash.
But it's on a, you wanted what?
On a wedge.
But it's a dash.
Yeah.
So can they do elimination?
No.
If they're on the same side, you don't have 180 degrees.
Mm-hmm.
Do you guys see that?
Yeah.
Yep.
So what about here? There's a hydrogen that is on a dash, but can we do elimination with these two?
No.
No, so no products. How about here?
One.
There's
one
a-
on the wedge.
Because those two are opposite.
Okay.
Agreed?
Mhm.
So if they do elimination, what's the product? Where's the double bond? Double bond is here. Isn't that right?
Yep.
What about that methyl? It is? Say it one more time. Why is it flat? Why can't I do this?
Because it
Because I will see it 20 times before it sticks in your head.
it's
Can't be.
there are free electron groups. It's trigonal planar.
It's flat. Absolutely. But then what about this guy?
Ethyl still on the wedge.
Same. Perfect. Ethyl stays the same because it didn't do anything. You guys agree?
Yep.
2 products there. Why 2 products here? Because this one has a hydrogen that's opposite, so this is going to create Did I do that correctly?
Mm-hmm.
But then the other one also has a hydrogen that's opposite, so therefore that can create. Is that okay?
Mm-hmm.
Does that make sense, everybody? For E2 to happen, the
Plus.
leaving group bond has to be opposite 180 degrees to the beta hydrogen carbon hydrogen bond. Otherwise, E2 cannot happen.
Interesting.
Everybody okay?
Yeah.
So that is E2. Any questions about E2? So remember, E2 is, let's just write it here. E2 is concerted, meaning no intermediate, which means you must show the transition state. E2 follows regioselectivity, follows the Zaitsev's rule, which means the more stable alkene is the major product. And E2 stereo selectivity, which means that the alpha carbon leaving group bond has to be opposite 180 degrees to the beta carbon hydrogen bond, must be anti. Otherwise, you can't do E2. Are we good with those points regarding E2? Yeah? Okay. What about E1? Let's talk about E1.
Is it more fun?
It's, I personally love E2. I don't know why.
Because
But
it's more fun.
Yeah, kinda. E1 is, I don't want to say it right now, but E1 is one of those things that's always there, therefore we never care about it. You know, one of your, okay, I shouldn't say that. No, I'm going to say that.
You didn't think about it, right?
Yeah, that's not appropriate. But you know how, okay, I can say this safely because some of us are moms here. You know how moms are always there, so you can just ignore them?
Thank you.
What's wrong with you? Isn't that right? So easy to take moms for granted because we're always there.
True.
Some of us suddenly gone into a feeling of depression right away. As soon as you think about that, it's like, oh, come on. But E1 is kind of like that. E1 is kind of like that because it's always there. And it's never the major one. It's never the thing that actually decides anything. It's one of the things that's always hanging around and who cares, and it's never the important one. But we should still think about it. We should at least still know what it's doing and how it's doing it. But it's definitely never the important one. So what does that mean? E means
Elimination.
what? Elimination. What does, and one stands for what, Carter? What did you say?
Unimolecular.
Okay, what does that mean? Unimolecular. What does that mean?
Only substrate is involved.
Exactly. Just like SN1, only the substrate affects the rate of the reaction. So E1 is very much like SN1, E2 is very much like SN2, E1 is like SN1. So SN1 is the mechanism concerted or step by step?
Step by step.
Cool. Similarly here also, it is not a concerted mechanism, it's a multiple step mechanism. What's the intermediate in SN1?
Carbocation.
Exactly the same here. Goes through a carbocation intermediate. In fact, that is also the rate determining step, just like SN1. No difference. Let's do something. So SN1, E1, very, very If you're doing SN1, you're also doing E1 because they're kind of the same thing and you can't escape it. So for example, can someone tell me what will be the SN1 product? SN1 product. Louder. Isopropyl. What? Oh, you mean alcohol?
Terbutanol.
Okay, but not isopropyl. That's a T-butyl group. But I think that's what you were trying to say. Is that right?
Yep.
Is that what you were saying? SN1, not E1. SN. Everybody agrees? SN1. Because you've seen it before. You've done it. Since you've done it before, can you tell me what the mechanism of this SN1 would be?
Chlorine
So
cuts off and it makes a isopropyl terbutyl carbocation.
Leaving group leaves, makes a carbocation. Agreed?
Yep.
Of course, chloride is there. Everyone okay? What's going to happen next? Can I just get rid of that for now? Yeah, it's there. We know it's there. What's going to happen to this now?
It reacts with the water.
Be more specific than that.
The oxygen on the water
Oxygen.
Do what?
is going to bond with
Because
oxygen on the water.
it's using its lone pair, act as a nucleophile, attack the carbocation. Attack meaning that it's giving the electrons. You guys with me? What does that create? Well, that creates this, which needs to go through
Acid-base reaction.
with water again, which will take a proton, give us the product. Everybody okay with that? Why are we doing SN1? We said we were doing E1. Because till this step, they are the same. Exact same. The rate determining step is making the carbocation. As soon as the carbocation is created, water has two choices. It can either act as a nucleophile, go in the direction of SN1, or anything that can be a nucleophile can also be a
Base.
base. Or it can act as a base, take the proton from the beta carbon, create the double bond, and make the elimination product. So it's really no surprise that wherever SN1 is, E1 will also be. No, you can't prevent it. However, here's the thing though. Is water a strong base? Have you ever thought of water as being a strong base? Is water a strong base?
It can be.
I'm seeing, well, it can be if you had a strong acid, right?
Yep.
Is that a strong acid
It's a
with
weak.
attached to carbon?
No.
So, is water a strong base?
No.
It's a weak base.
Very weak base. But is it a decent nucleophile? It's not a strong nucleophile, but with a carbocation. So which path will predominate? SN1 or E1? Always.
SN1.
Always. Whenever you do SN1, there will be E1. However, SN1 will always predominate, no matter what. Because that's a very poor base. What if we used a strong base? Well, then it won't be E1 anymore, it will do E2 instead. We'll get to that part later. The point is, SN1, E1 go together.
So it's the same thing.
Because the rate determining step is the same.
Yep.
This is where they take different paths. But now it's a question of, okay, a better nucleophile or a better base? Better nucleophile. So SN1 takes over, E1. There'll be a little bit of it, who cares? E1 will never be major, period. E1 will never be major.
Okay.
You guys with me? Everybody? But because it's there, can you tell me here's an example. I need you to give me all SN1 products and E1 products possible for something like this. What's the first step?
Make it a good.
Say that again.
Make it a
please,
good
ma'am.
living room.
And how will we make this a good leaving group?
H-water.
Acid-base reaction.
So can we be more specific, please?
Take the H.
Did you want the mechanism or the?
Yeah, we're writing the mechanism. So how do I show my curved arrows?
It,
Yeah?
The double-headed arrow from the H and HCl.
mhm.
You're saying this?
Or would it be the other way?
Careful, careful. Electrons. Curved arrows are about electrons. Curved arrows are not about atoms. That's not right. So what is the correct way to show that? The lone pairs on oxygen are taking a proton, and where are those electrons going? Exactly. So that way it becomes a better leaving group, because OH is a bad leaving group. Everybody okay?
Mm-hmm.
Of course there's Cl minus there too. Fine. I'll just say taken it out. Go. Okay?
Mm-hmm.
Now what else? What will happen next?
The water will break off from the
One of what will break off?
The wa-
Okay.
breaking off.
Okay. Good. It's a good leaving group now. It breaks off and creates a what?
a carbocation.
Everybody okay?
Mm-hmm.
Cool. Can this give us a product?
Yes.
Yep.
What would what would be the SN1 product from here?
That plus Cl in the plus.
Cl minus, okay. So if the Cl minus goes and attacks, you would get that. Am I right?
Yes.
Correct.
Okay. And what about E1?
The hydrogen will, since there's carbocations, but there's still a hydrogen, the hydrogen.
Which
will-
carbon? This carbon?
No, the one.
This carbon?
Yeah.
Right? That doesn't have, those are carbons, so it doesn't have hydrogens. You're right, this one does. So, Viola, one more time, what will this do?
It would, essentially, it would, one of the hydrogens would go over to where the chlorine without forming a third bond.
Very good. But why?
Uh,
Because the
Because-
base, oh, there's water. You can, that's a better base than Cl minus. The base is taking the proton, which is why those electrons are moving and creating the E1 product. Everybody okay? Is that it? Exactly. Carbocations, no matter which reaction you are talking about, if there is a carbocation, you must think about rearrangement. Can this carbocation rearrange to a more stable carbocation?
The
Yes.
plus and the methyl switch
Right there.
places.
So it goes through a methyl shift, which means, agreed?
Yep.
What would be the SN1 product from here?
Cl on where the plus is. Cl.
Everybody okay? What will be the E1 product from here? How many E1 products can you get? I'm using water as a base because water is a stronger base than chloride. Isn't that right? So how many E1 products can we get? Two. Why? Because there are two beta carbons with hydrogens on them. Do you agree that, of course, these are identical, right?
Mm-hmm.
But they have a hydrogen, but doesn't that also have a hydrogen?
Yep.
I was going to color. Okay, so if the water takes this proton and makes the double bond, what's the product? Do you guys agree?
Yeah.
But if the water takes this proton and makes the double bond, what's the product?
There'd be a double bond in the middle.
Do you guys all agree?
Yes.
Of these, if I asked you to tell me which substitution product will be the major product? Substitution product. Which? Say again? Because it's coming from the more stable carbocation, right? So that's the major SN1 product. Do you all agree?
Yep.
Which E1 product will be the major product?
The second one
Second one meaning
with the double
one?
bond.
this one, right? Compared to the black one?
Yeah.
Everybody agrees?
Yeah. It has 4 R groups on it.
Everybody okay so far? Now if I asked you with all of this analysis, of the two SN1, E1, which one is the major?
Well, SN1. Just
E1 is never the major, exactly. So don't choose E1 ever, because it will never be the major, can't be the major. So of the two, that is going to be a major. Are you guys okay?
Yep.
You've given me extra time today, so thank you. We'll stop here. What's our plan for Monday? The quiz on Monday will cover everything we've done since the exam. So mostly,
It's just
what have we
this.
done?
Just this.
E2, E1, this, right?
That's it.
And we went.
Didn't we do like, well, that's okay. Let's just focus on E2 and E1 for the quiz on Monday. And once we're done with the quiz, now we are ready to take all 4 of them together and do a comparison and then do some practice of how do you predict. Is it going to be SN1, SN2, E1, E2? How do we decide that? So that's going to be on Monday. I do think we can finish this chapter on Monday and also start the next chapter. I think next chapter is the alkene chapter. I forget the number. But that's probably
Yeah.
going to be my goal for Monday. Yes, Viola? But did I not give it to you? Oh, I just gave you a list
Verbally.
of topics. You want me to tell you how many points each thing is worth? Is that?
That's okay.
For me,
No.
everything is going to be full points if you've given a full effort to it, to be honest. It's more of a project without a rubric because it's more of us exploring. And who am I to say that I can actually assess any of this work? I don't know. Right? So, as long as we include these topics, we're good. By the way, there are some posters, some are good, some are actually not, that are on the notice board outside the lab. I don't know if you've seen them.
Yeah, I
Yeah.
did.
Same project, if that helps you.
But it's just like a sheet.
It's a poster board, I think.